Hey guys, so I'd just like to give you a kind of a talk through of what we did with the workshop, the enzyme kinetics kind of practice problem and the kind of real life research question example, and then what you might expect to see in an exam question, which really is just kind of what we did, but how I might phrase it. And just to remind you guys, the way that it's presented is that there's the concept of there's these four graphs which are kind of linked. And the first one is the concentration of things over time. And it may be, for instance, the concentration of, let's see, the concentration of product, which increases over time. Or on the other hand, the concentration of substrate, which decreases over time. And the idea that with these, as with anything where you're looking at a change over time, change in concentration over time. And we can look at the, where's my mouse? There it is. We can look at the slope there. And the slope is going to be equal to the rate, the change over time. Or alternatively, the velocity, which is kind of like, you know, the speed that your car's traveling over time. And if we were to look at this this rate, this change over time, if we were to plot how it might change at different concentrations of substrate, we can look at, let's look at the product. Let's look at the increase in product made over time. So we just look at the red line, the product over time. And we're going to look at how that would change over time as you change the concentration of substrate, which you add. And if you change the concentration of substrate, and let's say 0.1, 0.2, 0.5, and 1.0 micromolar of substrate, what we find is that as you add more substrate, you build up product faster if you look in the pre-steady state at the beginning. Because in the pre-steady state at the beginning, you're just looking at how fast the chemical reaction occurs. The chemical reaction is that the enzyme plus substrate comes together, forms an enzyme substrate complex, which then reacts to form the product, and then the enzyme and the product break apart, and you've restored your enzyme, so you can do the cycle all over again. But if you look in the if you look too late in the experiment, then the enzyme just becomes saturated, and it just you have to then wait for the enzyme is kind of saturated, and it reacts as fast as it can, and then it needs to break apart as fast as it can to free up some space so you can go around and do the reaction again. If you look in the pre-steady state, before the enzyme gets saturated, right at the beginning, then you have plenty of empty enzyme. You don't have to wait for some to free up at the end by kind of disassociating with the product. That way, you're not worrying about anything freeing up. You've already got it free up, and so you can just you can just watch how fast the product appears over time. So you're just looking at the speed of the chemical reaction rather than the speed at which it can break apart. And that's the part that we're most interested in. And as we increase the concentration of substrate, we'll find that that rate of that reaction there goes up faster. And it will keep going until eventually, actually, maybe we would have a concentration, let's say, for instance, 3 micromolar, where of concentration of substrate, where it doesn't really increase anymore, because it just gets saturated so quickly that it doesn't matter if you add more enzyme. You've got so much product that it can't go any faster. Adding more product's not going to make it go any faster. So we've already kind of reached our maximal rate. And what we want to do is that we want to look at this initial velocity, this pre-steady state, and we want to see how fast the reaction happens. So we're just looking at this part here. We're not limited by how much free enzyme there is. We can just look at the initial reaction, which is this part here. And again, we're looking at the slope, which is going to be the change over time, the change over time. And you'll notice that it gets steeper. You know, this is getting steeper as we go up. And so if we were to plot another graph now that looks at that steepness, which is the velocity, because if it's steeper, then it's a bigger change over less time. That's what steepness is. We look at this, how the steepness increases as the concentration of substrate increases, then we'll see that it will increase linearly at first, but then it will level up and plateau. And this happens because you've added so much substrate that it just very quickly reaches that saturated step, that steady state so quickly that it just immediately goes to its maximal speed. And so we know what its maximal speed is, and adding more won't make it go faster. We've already just completely saturated it. And whatever this speed is, where we've added so much substrate that you've reached the fastest that it can go and it's saturated, whatever this speed is the Vmax. And and the units of that are going to be rate, so it's going to be a change over time. Whereas, of course, the substrate concentration is just the concentration. We take the whatever the Vmax is, whatever the maximal half speed is, whatever the maximal speed is, we half it. We look at the concentration of substrate required to half it. That's going to be the Km, which is the concentration required to hit half maximal velocity. And there's a few reasons why we do this, but the idea is it's describing a more efficient kind of fuel in a roundabout way. It's saying that if you require kind of imagine, forget for just a moment that it's the half maximal speed. If you think of it as being just maximal speed, you can say, well, a substrate which requires less to make it hit its maximal speed is a more efficient substrate. And the reason why we decide to do it with half, and so half is going to be the same thing. And we just do that because sometimes it's not clear what the maximal speed is. And so we can just kind of say, well, we look at half maximal speed, and that's often a little bit easier to figure out and a little bit easier to compare. And if we had two different substrates, and let's say that one has got the black line Vmax, but the other one, it increases slower, we can actually say that if we look at the Vmax is the same, but we go to the concentration required to hit half Vmax, it's further along, so it's a bigger number. And so notice that it's less steep. Well, that's kind of saying that it's less efficient. It requires more in order to get it going. And so a bigger Km, a higher concentration, is reflecting that it's a less efficient fuel. And so sometimes even when we're talking about enzymatic reactions, and we've got maybe glucose and fructose, and the glucose has got a Km value of 0.1 micromolar, and the fructose has a 0.2 micromolar. We can say that glucose is the more efficient fuel because the Km is lower, and that's reflecting that less is required to reach its half maximal speed. And so it's saying that it's speeding up faster. It's better to catch it in this kind of logarithmic growth phase than to catch it at the end, because sometimes it's not always clear where the end is. So it's saying that the glucose is the more efficient one. Or sometimes even if we've got, for instance, the reaction of glucose to glucose 6-phosphate catalyzed by the enzyme hexokinase, and glucose might, for instance, have a Km value of 0.1, and glucose 6-phosphate might have a Km value of 0.2 micromolar. Because remember, it's a reversible reaction. So glucose can bind as the substrate and generate glucose 6-phosphate as the product, but glucose 6-phosphate could bind as the substrate and generate glucose as the product, because these are reversible reactions. Remember, these are enzymatic reversible reactions. And let's say that as biochemists, we want to know, well, in the body, which is the one which is going to be the direction in which it goes. Or we can say, well, it's probably going to go in this direction because this is the favored, more efficient substrate. So that's an important thing to remember there. So once we've generated, remember I said that these three graphs, once we've generated these three graphs, that can often be enough information to tell us everything that we want. But this graph here, which is essentially the V0 equals V max substrate concentration over substrate concentration plus Km. Now let's may I erase? Yeah. Plus Km, the Michaelis-Menten equation. This is just the graph of this equation here. And sometimes it can be awkward to work with curves. So we can convert the curve into a straight line equation, which is going to just, to do that, we just take these numbers and just do 1 divided by what all of these numbers are. So if this curve is made up of a series of points, if we just take each one of those individual points and just whatever the velocity is at the certain substrate concentration, and just do 1 over that velocity, 1 over that substrate concentration, and then plot it as another graph, it'll convert that curve into a straight line. And it's kind of like a trick of math. If you have a curve, you just do 1 over each number on the x and the y axis, and then replot it. That's awful, isn't it? It'll give you a curve instead. Let's try and get that a little bit straighter. It'll give you a straight line instead. And so this was the V0, and it's now 1 over V0. And this was the substrate concentration, but it's now 1 over substrate concentration. And what we can do is that we can then, rather than having to draw lines on pieces of paper in order to figure out Vmax and then half Vmax, what we can do instead is that if we plot it, let's do a different color to make it nice and clear. If we were to plot it on a graph instead, what we would have is a straight line. And because it's a straight line, it follows the basic scheme of a straight line graph of y equals mx plus b, or c, whichever way you were taught it. And where the c intercept is, that is 1 over V max, and where the x-axis intercept is, that's minus 1 over Km. And the slope can be is a mixture of the Vmax and the Km. We can use that to figure out each of these, because if we know some of these points on here, we can change the equation to isolate it. For instance, to isolate each individual point to find out what it is. For instance, let's say that we want to find out what x is. We could make x the subject, and we could do y take b divided by m equals x. We could just rearrange it to find out all the individual points. Whereas with this equation, you have to kind of draw points on a graph, which isn't really very accurate. The Lineweaver Burke plot uses the linear regression. It's a little bit old-fashioned with what we used to do back in the 60s, but it allows us to figure out a lot of these points and constants. Now, nowadays, you can just program a computer, and it can just work things out for you on this point. But sometimes if you want a quick answer, you can just use a Lineweaver Burke plot. But finally, one little caveat is just that sometimes a Lineweaver Burke plot can give you more information, because sometimes often in real life, the data isn't perfect. And maybe, for instance, you can plot your graph with a curve, and it comes out, and let's say that it comes out like this. This is this graph up here. But let's kind of say what it might look in real life. It may look like this. So here the question is, what is the Vmax? Because it's actually kind of difficult to know what the Vmax is. Maybe it levels out here, or maybe it keeps going. It's really kind of, it's not clear. So, but what you can often do instead is that you can use the Lineweaver-Burke plot to, instead of having V0 against S, again, you can plot it as 1 over, and it will give you the straight line, and then Vmax can be worked out as just being the intercept. So it can be really, really handy for sometimes if you've got non-perfect data to try and get a better idea of what's going on. And then once you've got a better idea of what's going on, then you can go back and refine your method, your experimental method. Because you've got once you've got kind of a ballpark idea of what the Vmax is, then you can kind of change and tweak your experiment in order to get the better data. So you could kind of use your perfect graph eventually, but you want to ballpark it. Or often with things like chemical inhibitors. Because if we've got a chemical inhibitor, we plot it on a Lineweaver-Burke plot, depending on the type of chemical inhibitor. Remember, we looked at 2 types. Maybe it is a uncompetitive inhibitor. And if we were to plot the change in initial velocity at different substrate concentrations, at different concentrations of chemical inhibitor, concentration 1, 2, and 3. So that means that we do 3 sets of reactions, one with substrate plus enzyme, and then measuring the product over time. And we'll do that with 1 concentration, and we'll do several concentrations of substrate with no inhibitor, and do it again with a little bit of an inhibitor, and then do it again with a little bit more of an inhibitor. And each time you plot it with the 1, 2, and the 3 different types of chemical inhibitor, you'll be able to see that change over time. So yeah, it's a lot of experiments, but then it creates a very, very easy to understand graph. We can say, oh, well, we know for a fact now that Km is not changing, but Vmax is changing. Therefore, this is an uncompetitive inhibitor. Whereas if you were to do this again, but you were to find that it forms something like this, and you can see that the Vmax has not changed, but the Km has changed. So it is a competitive inhibitor. And that's really, really clear on a Lineweaver-Burke. Whereas on something like this, it often is not very clear. And the computer can make a guess, but sometimes the computer gets it wrong, especially if your data is not perfect, because you're trying to figure this out. Because if it was easy, someone would have already done it. That's why you're doing it. You're doing it because it's hard. So it can give you, so first to summarize, when we work out enzyme kinetics, we'll often go through 1, 2, 3, 4 different graphs in order to figure things out. We're looking the change of product over time at different concentrations of substrate. We can then plot it onto this curved graph here with the Michaelis-Menten equation. And depending on how the data looks, we may or may not be able to do computer nonlinear regression, which would be able to figure out the Vmax and the Km and things like that. But if we can't do that, we don't want to do that, we can do the linear regression of 1 over V0, 1 over substrate concentration. That'll give us a straight line equation instead, which is much easier to work with. And it's not perfect because when you do this nonlinear regression, you kind of lose data and you kind of make some kind of assumptions about things. But in general, it's a pretty good estimate. And that can, and the Lineweaver-Burke plot can sometimes be better, especially if your data isn't perfect, allowing you to go back and refine your data. But in general, it'll be a very good ballpark figure. It'll be pretty close. But in particular, where it shines is when you want to apply it to a chemical inhibitor, where it can very easily actually tell you what type of chemical inhibitor you've got, and often night and day what type of chemical inhibitor you've got, which is super important. So how will we go and apply this to a question? Okay, so this is the question that we had in class. And if we were to, the question is saying like that we have this enzyme here, malate dehydrogenase, which is part of the citric acid cycle, converts malate to oxaloacetate. And malate is a substrate, oxaloacetate is a product. And we want to measure the rate at which we turn this substrate into product. So the rate at which the product builds up and the velocity. And then from that, we can work out the Bmax and the Km, and also later on the Kcat. And of course, once we have the initial velocity, we can use that to work out the Vmax and the Km. Yeah. And so the malate and the oxaloacetate, they don't have they are very hard to detect. We can't look at them spectrophotometry because we're using spectrophotometry because they don't absorb light in a particular wavelength particularly well. But also, what is substrates in this are also what is a substrate in this is also NAD. What is a product? It's NADH. Because what's happening is that this bond here is being oxidized, transferring electron from the oxidized NAD, ending so this becomes oxidized. This oxidized thing becomes reduced, generating the reduced NADH and the oxidized oxaloacetate. That's what happens in the TCA cycle. And then this NADH gets used for the electron transport chain. And so essentially you're steaming electrons from malate to put them into the electron transport chain via the carrier NADH. Anyway, the point is that NADH absorbs light at 340 nanometers. So we can use the Beer-Lambert law, which is absorbance is equal to the molar coefficient times the concentration times the path length, which is just the idea that if we have a vessel which has got some liquid in it that absorbs light, we shine some light through it, some of that light will be absorbed by the compound. And so less goes through. And so we can work out by how much less goes through what the absorbance of the compound is. And of course, if you have it thicker or thinner, then more or less will be absorbed. And we can, if we know the molar coefficient, which you do, which is just a constant saying how much each thing absorbs light. For instance, say that apple juice might absorb less light than orange juice at the same concentration. Then you can rearrange the equation here. Oh, and path length, like I said, is how you know, if you have a thicker path length, it's going to obviously there's more of it to absorb, but path length is usually assumed to be 1, because in a lab we just use a 1 centimeter cuvette path length usually. So we can rearrange the equation for to make it absorbance divided by the molar coefficient equals the concentration. And it's actually the molar coefficient times L, but because L is 1, we can just disregard it. So if these, I'll get to, well, so we can use the Beer-Lambert law, and we can just measure the concentration, the changing concentration of NADH over time as a proxy for the, well, the enzyme overall, because this is product and this all is substrate. So what the experimenter has done is looked at the product as as NADH over time, which is this graph here. Now these are absorbances, but we can convert them into concentrations to give us the change in concentration over time. At the moment, it's absorbance over time, but we can turn absorbance into concentration really, really easily. And then this is different concentrations of substrate. And what you may be able to see is that at the low concentration of substrate, it increases slower. And at the high concentration of substrate, it increases faster. Indicating that, you know, the absorbance goes up slower, goes up faster, and therefore the concentration goes up slower or goes up faster as we increase the concentration of substrate. And so if we were to plot that, or do all of these individual conversions, we take the absorbance values of each thing, and we can divide it by the molar coefficient. A divided by molar coefficient equals C. This is now the concentration. And then remember, the molar coefficient was in millimolar. And so what this number would have been 0.355 divided by 6.22. And that's actually going to give you 0.057 millimolar, because the units here are millimolar. That's kind of a weird number to work with. So we'll just times it by 1000 to turn it into 57. And this will be 0.1. And it's going to, therefore, the units are going to go from millimolar to micromolar. So 57.1 micromolar. We just do that for every single one. And then, so that's therefore going to give us the product in micromolar now, made over time at different concentrations of substrate. And you can see clearly this increases from in 10 seconds you made 9.3 micromolar, and then when you doubled the concentration, it made 17. You increase it to 5, it's 31, 41, 57. And you can watch the change over time. And if you were to plot every single one of these, so this will be X, this will be Y1, Y2, Y3, Y4, Y5. You get 5 different graphs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And what you would find is that it would, I've not done it very well. I'm trying to show that this is kind of less steep, more steep, more steep, more steep, more steep, as reflecting that these numbers are getting steeper. So you're making more product over time. I remember product over time equals velocity. And so you get something that looks like this. I remember we want to look at the initial velocity. So you can, it's up to you whether or not you take the initial velocity as being here or being here. I think I did it as being, actually, I believe I did it as being here. But either looks like it's in the pre-steady state versus the steady state, and we want the pre-steady state because we're not worried about EP breakdown to E plus P, and we're just looking at the ES to EP, which is our so-called K2, because this will be K3, and the E plus S is K1, part 1, part 2, part 3. 3 parts to the reaction. So we can look at the individual slopes here and see that they're getting steeper, and slope is product over time, which is velocity. And since we're looking at the initial slope, we're looking at the initial velocity. And if we get Excel to tell us what those numbers are, we could work it out ourselves as rise over run. And we can figure out that number ourselves, but we can just tell Excel to do it. And this will give us the slope. And we can see that the slope, the steepness of the slope, therefore the velocity, initial velocity, is increasing as the substrate concentration increases. And if we were to then plot that, so these numbers here, 1, 2, 5, 10, 25, 1, 2, 5, 10, 25, and the slope, which is our V0, 0.9, 0.1, 3.2, 0.9, 1.7, 3.2. And if we plot that, 1, 2, 3, 1, 2, 3. If we were to plot that, it gives us a graph like this. But remember what I was saying. Where is Vmax? You could say Vmax is here. How do you know it's not here? Right? It's not awfully clear. So we can make a guess about Vmax and then half it, make a guess about Km. But if our Vmax is actually here, then actually it's going to be off of our Km too. So this is, this is showing the kind of the error in doing it like this, that the data is incomplete. It's not perfect. So it's going to, it really needs to be extended out or redone. So, but what we can do instead is if we just take each of these numbers and just do 1 over each of these numbers, we can generate this. So this is just 1 over 1, 1 over 2, 1 over 5, 1 over 10, and 1 over 932, 1 over 1704, 1 over 3.183. And if we plot that, 1, 2, 3, 1, 2, 3. Actually, that's a lie. Sorry, it's 1, 2, 3. It's the other way around. Might be. But you can see that it creates this nice straight line. And now the straight line where it intercepts, that is 1 over B max. And where it intercepts here, that is minus 1 over Km. And you can also use the slope as well. And that's what we do here. We can figure out, we can rearrange the equation in order to make C. Because it's a straight line graph, it's the straight line equation. We can rearrange to find C or B, whichever one you use. And so we can figure out the slope as rise over run. We can either get Excel to tell us what it is, or we can figure it out ourselves. Rise over run. It's going to give us the slope. So the rise is this much, the run is this much. So this is how much it rises. This is how much it goes across. So it's just let's see. Oh yeah, so so this is let's say A, B, and so A minus B is going to give us the distance between them, and the same thing. Let's call this X, and no, let's not call it X. Let's call it C and D. C, D, and the difference between, if we just do C minus D, then that will give us the difference between them. So that will be the total rise and the total run. And if we divide them, then that gives us the slope, because that's how much it changes per. So that's the slope. And the slope is equal to the Km over V max on a line weaver plot. And if we then, now we know the slope, we know the M value, and then we can just plug in Y and X, or any Y and X, and it will give us B. And B is equal to 1 over V max. So 1 over B will give us the V max. And now that we have the V max and the slope, we can just rearrange this equation here. V max times slope equals Km, and boom, there's the Km. And if we want, we can work out the x-intercept, which is more fiddly to do, but x-intercept is equal to, it's the intercept when at x. And so if we set x to 0, x as 0 minus c divided by m equals the point at which it intercepts at y, which is the x intercept. So if we plug that into here, then that gives us negative, the x-intercept here as negative 0.154. And if we do negative 1 over 0.154, that gives us 6.47, which is the Km, which is right. So it's right, that is what the Km is. So to summarize, what we've done, or what we would do if we wanted to do this experimentally, what we would do is, let's say we've been given an enzyme. Let's go back to the beginning. We've been given an enzyme. What we're going to do is that we're going to measure the concentration in product over time. So let's say that if I posed you guys the question, you are given an enzyme and a substrate, and you know what the product is, and you want to measure the Vmax, the Km, and the Kcat. I'll tell you guys about Kcat in just a moment. How would you do that? I would say, right, you would look for the increase in product over time. And if the product is, you want a product which is visible by spectrophotometry, either because it contains NADH, or where's my pen? Either because it contains NADH or another product, which is visible by spectrophotometry, and you would look at the increase in product over time, and using the Beer-Lambert law if necessary. Once you have the increase in product over time, you can look at that with different concentrations of substrate, and from that you can derive the slope of the. You can look at the graph, this work out where the pre-steady state is, and then get the slope of the pre-steady state. And then you can plot the slope of the pre-steady state at different concentrations of substrate. And then if the answer isn't obvious there, then you can replot it as a Lineweaver-Burke plot, and then read the Lineweaver-Burke plot to get the Vmax and the Km. So it's that simple. You just you just look how you would do it. Look at the concentration in product made over time at different concentrations of substrates, and then plot it, either use non-linear regression if you have a complete model, or use linear regression if you don't have a complete model, such as the Lineweaver-Burke plot, and then use that to figure out the constants. And then once you have the Vmax, I promise I say the Kcat, the turnover number, that's the number of molecules made per second. Kcat is equal to Vmax divided by the enzyme concentration. So we have the Vmax as 6.97 micromolar per second, and the concentration of the enzyme is 10 nanomolar. Therefore, we convert it into 0.01 micromolar, so that the units are the same. And I'll give you the answer. I don't know. Let me think. That's going to be, my guess is 697. I think that's right, because it's just going to move the decimal point 2 places. So it'll be 697, and the units are second. So to find the Kcat, the turnover number, the number of molecules made per second, the Vmax divided by the concentration of enzyme, make sure your units are correct, and you have the units correct as being both in the same units. You could have converted both into nanomolar, convert both into millimolar, convert both into micromolar. Doesn't matter, as long as the units are matched up, and it'll give you an answer in number of molecules per second. Make sure you've got that. And that's how you would figure that all out. And then finally, if you wanted to figure that out for an inhibitor, what you would do is that you would do the, let's say, the time at different, 0, 10, 20, 30, 45, 60, and you would have the substrate concentration of, let's say, 0.1, 0.2, 0.3, and you would plot that to get 1, but then you would do the same thing. So substrate of 0.1, 0.2, 0.3 micromolar, but you would then add some inhibitor, and then you would do it the same, but then add some inhibitor at a, where's my pen? At a different concentration. And that way you would have 1, let's say just I0, so that's no inhibitor, some inhibitor, some more inhibitor, and then you can look at where where it intersects, whether or not they intersect at this x-axis, the y-axis, or the c-axis, generating a uncompetitive or a competitive inhibitor, and that can tell you the type of inhibitor that you have as well. And also, what I didn't teach you guys is that by going off the shapes of these graphs as well, you can work out Ki values, which is how efficient the inhibitor is. But I didn't go over that in this class. But you could also derive those values from the shape of this graph. So how would you do it if you had an inhibitor? You do exactly the same as without an inhibitor, but you just repeat it at different concentrations of inhibitor to draw multiple lines on your line wave plot. And that covers that. So if you have any further questions, please shoot me an email. I'll be glad to help out with that. And I hope you have a great rest of your day.